Okay guys, today we're going to talk about applications of tree diagrams, and we're going to begin with this interesting word problem that I have here, so I'll just kind of read it with you. So it says the ELISA test is used to screen donated blood for the presence of HIV antibodies. So this is a test for determining whether or not someone has an HIV infection. When HIV antibodies are present in the blood tested, ELISA gives a positive result 98% of the time. So you might remember from biology, antibodies are what your body creates to fight off an infection. So the presence of antibodies in the blood indicates that there is an HIV infection. So this sentence here is just saying that when there's an HIV infection, ELISA gives a positive result 98% of the time. When HIV antibodies are not present in the blood tested, in other words, when there's no infection, ELISA gives a positive result 7% of the time, which is called a false positive. It would be a false positive because there are no antibodies in the blood, in other words, there is no infection, and yet the test is still saying that there's an infection. So that is a false positive. Finally, suppose that 1 out of every 1,000 units of donated blood actually contains HIV antibodies. I suppose that means that something like 1 out of every 1,000 people in the population has an HIV infection. And here's the question. What is the probability that a positive ELISA result is accurate? Okay, so the ELISA test is a real test, but the numbers are a little bit fictitious, but they are more or less sort of in the ballpark of the real figures. And what I'm going to do to answer this question is I'm going to draw a tree diagram. Okay, the first thing that we need to sort of recognize is that there are multiple sort of decisions that have to be made, or splits in the diagram. One thing that can happen, obviously, is the person can have the disease or not, right? They can have the HIV infection or not. And then beyond that, whether they have the infection or not, they could test positive or test negative, because the test isn't perfect, right? It makes mistakes. So there are really sort of like two splits that we're going to see in our diagram, one corresponding to whether or not the person has the disease, and whether or not the person tests positive or negative. We have to make a decision about what our first split represents, right? Should we make our first split represent testing positive or negative, or should it represent having the disease or not? The answer is we should make it represent having the disease or not. And the reason for that is the following. In this problem, and in every problem like it, your first split in the tree diagram should correspond to the factor which is causing or influencing the other. It is the presence or non-presence of the disease which affects and influences and causes the outcome of the test, not the other way around. And because it is the presence of the disease or the non-presence of the disease which is affecting the positive or negative test result, it is your disease and non-disease that should correspond to the first split. In other words, the first split in your tree diagram should correspond to the action, to the event, which is causing or influencing the other event. Okay? So cause and then effect. All right. For short, in my notation, I'm going to represent disease as a capital D, and I'll represent no disease as a capital N. Okay, so after that we have another split, right? The tree diagram splits again because the person could test positive, right? The ELISA result could say that the person is testing positive, or they could test negative. And then same thing here, right? They could not have an infection, but the result could still be positive, or they could not have the infection and the result could test negative. The next thing we need to do is place some numbers on this diagram. We need to write the probabilities of each of these events on the diagram. So let's have a look at the data that we've been given in the word problem and try to figure out where each thing goes. So scanning through the problem quickly, the first number that I see is 98% of the time. What is that? It says when HIV antibodies are present in the blood, ELISA gives a positive result 98% of the time. So that's saying that assuming or given that there's an HIV infection, ELISA will be positive 98% of the time. I claim that that is the probability that the test will come out positive given the fact that the person has the disease. So let's just make sure we understand why this 0.98, this 98% number, is this. If you assume that HIV antibodies are in the blood, in other words, if you assume that the person has a disease, so given the fact that they have the disease, the probability that the test will come out positive is 98% of the time. That's exactly what this is, the probability of the test coming out positive given the fact that they have a disease. So that's this figure here. And where does that go in the diagram? You might remember the given probabilities all sort of appear here. The 0.98 figure is actually going to be right here, 0.98. That's the probability that the person tests positive given the fact that they are on that branch here, given the fact that they have the disease. All right, what else do we see? The next number that appears is this 7% figure. So what is this about? It says, when HIV antibodies are not present, ELISA gives a positive result 7% of the time. Okay, that's saying that given the fact that the person has no disease, given the fact that there's no disease, the probability that they will test positive anyway is 0.7. So that's the probability that you'll get a positive test result given the fact that they have no disease. That's what this thing is here. And where does that appear in the diagram? It's going to be right down here. The probability that they test positive given the fact that they have no disease. So that's 0.07. And then finally, one more number. We have this 1 out of every 1,000 thing. It says 1 out of every 1,000 units of donated blood actually contain HIV antibodies. So where is that 1 out of 1,000 number going to go? That's the probability that a random person has a disease, which is this number right here. That's 1 out of 1,000, which if you write 1 out of 1,000 as a decimal, it's 0.001, right? 10, 100,000? Yeah. Okay. So we've now incorporated all of the numerical information that we've been given into the diagram, but before you go any further, you really need to fill out the rest of this diagram. So for one thing, this branch here can be computed by recognizing that this probability plus this probability has to add up to 100%. Okay, if the probability of having the disease is 0.001, then not having the disease is 0.999. And then the same thing here. Assuming that the person has the disease, if there's a 98% chance that they'll test positive, there's a 2% chance that they'll test negative. So 0.02 here. And then finally, same idea down here. Assuming they have no disease, the probability that they test positive, 0.07. Therefore, the probability that they test negative must be 0.93, the remainder. And then if you remember, there's one more thing we have to compute. That's the end branch probabilities, the numbers at the end of each of the branches. And those numbers are going to be the product of all of the numbers along the path. So this number right here is going to be 0.001 times 0.98. So that's going to be, let's see, so 0.00098. Yeah. Okay, and then this one here, we're going to add another 3 zeros here. If you multiply these two numbers, we get 0.00002, right? And then here, 0.999 times 0.07, that's going to be 0.06993, and then finally these two guys here, 0.997 times 0.93 gives me 0.92907. Okay, so we've completed our tree diagram, and now we have to answer the question, or try. it says, what is the probability that a positive ELISA result is accurate? So that, believe it or not, is asking, what is the probability given the fact? So, I mean, the probability that a positive ELISA result is accurate, what we're saying really is, given the fact that the ELISA result came up positive, given the fact that the test came up positive, what's the probability that it's accurate? In other words, given the fact that the test came up positive, what's the probability that the person actually had the disease? So the question that we're looking for here is the probability that they actually have the disease given the fact that the test came up positive, right? Which, notice, that's different from this thing here, right? The probability that they test positive given the fact that they have the disease, that's something we were given directly in the problem. But the probability that they have the disease given the fact that the test came up positive, that's something that we haven't been given the information for. We have to calculate that. Now, what you'll sort of notice is the expression for this doesn't really appear anywhere in the diagram, right? The conditions are kind of backwards. We know this, right, for sure. That's the 0.98 figure right here. But this guy here, probability that they have the disease given the fact that they're positive, that one we don't really have. What we have to do is we have to use a formula, okay? And what I'm going to do is I'm going to recall the AND probability formula that I introduced a few days ago. If you remember, the probability of A and B is the probability of A times the probability of B given A. You might remember this is sort of the formula that we used for the probability of consecutive events, like one thing happening after another. It really says the probability of A happening and then B happening is the probability of A times the probability of B happening given that A has already occurred. What we can do is we can solve this equation for this expression here. You actually did this in the homework exercise. If you do that, you find P of A given B, or sorry, A intersect B, over P of A is equal to P of B given A. So that formula right there is what we can use to solve this problem. So quick description of what's happening here. In these tricky word problems, you will often be asked to compute something like this, some given probability. But the given probability is kind of the wrong way around, right? Like, as I said before, we know what this is. That's in the diagram. That's this guy right here, the 0.98 figure. But here, the given thing is sort of the wrong way around, right? When you're asked to compute something like this, you need to use this formula, okay? So let's use our formula. The probability of the person having the disease, given the fact that they tested positive, is going to be equal to what? So according to this formula, I'm sort of reading it in this direction. According to this formula, it's going to be the probability of the intersection of the two events, that means disease intersect positive, divided by the probability of the given thing. That's the probability of positive. I want to make clear this formula can be a little hard to interpret. Sometimes it's easy to get like the A's and B's all mixed up. Just remember that it says the probability of one thing given another is equal to the probability of the intersection, just both events happening, divided by the probability of the given thing, right? A is the given event in this formula, so you're dividing by the probability of the given thing, and that's what I'm doing here. It's just the probability of D intersect plus divided by the probability of the given thing. That would be the plus there. All right, so we should be able to compute all these things. So probability of both D and plus. If you remember intersections, right, D and plus or D and minus, intersections are the end branch probabilities, right? So where is probability of disease and testing positive? That's this figure right here. Okay, that's the probability of disease and positive. So that's our numerator, 0.00098. Over the probability of being positive. Now, if you remember, probability of being positive, that's a little tricky because there are actually two different branches corresponding to that event. And if you remember what we said previously, whenever there are multiple branches corresponding to an event, you need to add together all of the end branch probabilities associated with that event. And there are two of those, right? These two guys right here. So probability of testing positive is going to be this plus this. So that's 0.00098 plus 0.06993. Okay, and now I'll ask my calculator, what is that exactly? 0.00098 divided by 0.00098 plus 0.06993 gives me 0.0138 approximately. So that's like a little bit more than 1%. It's like about 1.38%. That's pretty low. Let's remember what this question was actually asking. It said, what's the probability that a positive ELISA result is accurate? And it turns out the probability that a positive ELISA result is accurate is extremely small, 1.38%. So what that's saying is if you take this test and it comes out positive, it is very unlikely that you actually have the disease. Sounds like this is a terrible test. The truth is it's not. It's actually a very good test. And to see why it's a good test, we have to answer the next question. The next question says, what is the probability that a negative result is accurate? Right? Okay, so let's run through the whole thing again, except, computing this guy here. Most of the work is already done from the first problem. So first of all, the probability that a negative result is accurate, what is that really? It's saying, assuming that the test comes back negative, given the fact that the test comes back negative, what's the probability the person is actually free of the disease? What's the probability that the person doesn't have a disease? So this is the probability that the person has no disease given the fact that the test came back negative. That's what it's asking, okay? Now if we look at our tree diagram, once again, this figure does not directly appear in the tree diagram. The probability of having no disease given the fact that the test came back negative doesn't appear. You might be thinking, oh, isn't that this figure? No, that figure right there, that's the probability that the test comes back negative given the fact that they have no disease. You can see that the conditional is kind of the wrong way around, right? And as I said last time, whenever your given probability is sort of backwards, you need to use this formula, right? So let's use the formula to compute probability of n given minus. So probability of n given minus. The formula says it's the probability of the intersection, n intersect minus, so that's both no disease and test coming back negative, divided by the probability of the given thing. So that's the probability of negative. Now this guy here, the numerator, that's an AND probability, that's an intersect probability. That's one of the end branch probability numbers, right? It happens to be, let's see, n and minus, that's no disease, and negative, that's actually this one here, the 0.92907. Okay, so 0.92907. Over probability of testing negative, once again, testing negative is associated with multiple branches in the tree diagram, right? This one here and also this one here. And whenever you have multiple branches associated with an outcome, you need to add them together. So that's going to be 0.00002 plus 0.92907. Okay? So whatever this is. So if we compute it, 0.92907 over 0.00002 plus 0.92907, I get 0.999978, okay, which is very close to 100%. That's like 99.9978%. That's the probability that a negative test result is accurate. So here's the question. The test seems to be very inaccurate when it produces positive results, right? Positive results are almost always wrong, right? If you get a positive result for your test, it's very unlikely that you actually have the disease. On the other hand, negative test results are extremely accurate. If this thing gives you a negative test result, then you almost certainly do not have the disease. So this is accurate in one way, namely this way, but very inaccurate in another way. And you have to ask yourself, which is more important? The answer is this. This figure is more important. From a health perspective, you know, a false positive like this, you go in, you take the test, you get a positive test result, but you don't actually have the disease. That scares the patient, right? But all that happens is the patient goes and takes another test, and probably in the next test they'll find, oh, you don't really have a disease, and that's the end of the story. So this figure being low is not such a big deal. Basically, you give the patient a scare until they take another test, and they verify, oh, you don't actually have the disease. On the other hand, this had better be very accurate. If this is wrong, right? In other words, if the test result comes back negative, that patient had better not have the disease, because if the test result comes back negative and they actually do have the disease, then they're not going to take any precautions for themselves. They're not going to undergo any kind of treatment, and so they're going to get very sick. And also, if the disease is contagious, which in this case, of course, it is, they could unknowingly spread the disease. So it's much more important that this figure be very high. And as a matter of fact, these two figures are kind of, it's a bit like a virus scanner on your computer turned up to be very sensitive. It's like constantly finding viruses that aren't really there. It's like saying, you've got a virus, even when you don't. Producing all those false positives is necessary in order to find every single true virus. That's basically the idea behind all of this. Okay, so the only other thing that I want to talk about in this lesson is a very short thing. It's kind of an oddball topic that just appears at the end of probability, but it's a neat topic, and it's really easy to do. So I'll just explain it very quickly. It's called expected value. So suppose you play the following game. You roll a die, and you win or lose money depending upon what happens. So you're gambling, basically. So here are the possible die rolls, right? And here are the payoffs. So you roll this die. If you get a 1, 2, or 3, then you win $2. If you get a 4 or 5, you lose $10. And if you get a 6, then you win $20. The question is basically, should you play this game or not? Well, what we want to do is figure out how much you can expect to win or lose on average, right? How much can you expect to win or lose? And the way that you do this is you basically just take each payoff and you multiply by the probability of that payoff occurring, right? So the first payoff is $2. So you could win $2, but what's the probability of that outcome occurring? It's 3 out of 6, right? That would be 1/2. And then the next thing that could occur is you could lose $10. Oops, this expression is wrong. Let me go ahead and do it again properly. So you could win $2, so that's $2, times the probability of that outcome occurring, which is 3 out of 6. The next thing that could occur is you could lose $10, right? So you could subtract $10. You would subtract $10 times the probability of that outcome occurring. That would be 2 out of 6. And then finally, the last thing that could happen is you could win $20. That's plus 20 times the probability of that outcome occurring. So that's 1 out of 6. So and whatever this is, that's the expected value. So the idea with expected value is you just look at each possible payoff, every possible gain or loss. You multiply each payoff by the probability of it occurring, and then you add them all up together. And losses you treat as being negative. So if we actually compute all of this, this term is really just 1. This term here is actually just 10/3. This term here is also 10/3 if you compute it, because 20 out of 6, 10/3. So these two terms cancel, and you're left with 1. Now, what is that telling you? It's telling you that on average you can expect to win $1 when you play this game. Now, it's actually not possible to win exactly $1. What it's saying is if you play this game a million, billion, trillion times, and you take the average of all of your wins and losses, then on average you'll have won $1. What this means is that you should play this game, because sometimes you'll win and sometimes you'll lose, but on average you gain $1 per game. So you should be playing it. If this came out to be a negative value, that would indicate that you'd be losing money on average each time you play. And finally, we sometimes say that a game is fair if the expected value is 0. Okay, so a fair game means that the expected value is 0, because it means on average you're not going to gain or lose money, right? Sometimes you'll win, sometimes you'll lose, but on average it comes out even. Okay, so that's it.